Uh, Hello, everyone, and welcome to another, it's a great RISC-V technical session. Today, we are happy to bring to you Dorami, privileged separating security monitor designed for RISC-V trusted execution environment. Our presenters today here are Mark Kuhn, PhD student at ETH Zurich, Stravos Wallace, researcher at Microsoft, and Shuita Shinde, uh, who is a assistant professor at ETH Zurich. So without further ado, the stage is yours.
All right. Yeah. Thank you very much for the nice introduction and for inviting us. Welcome everyone. In today's technical session, we will take a closer look on software that executes in RISC-V in the M mode. And more specifically, we will show with Dorami a new approach how we can strengthen security guarantees for TEEs using a privilege separation approach. All right, so let's directly start with a short overview for the concept of TEEs and how they can be deployed on RISC-V. All right, so yeah, let's take a look on a typical app deployment as we would find it, for example, in a cloud service scenario. So here we have our app that, for example, could process some sensitive user data, for example, some banking or some other personal data of users. Now, this app might itself be written very well. For example, it could use some encryption or some other mechanisms to protect itself against attacks or use some memory safe languages. However, it executes alongside many other apps that are also deployed inside of the cloud server. And this could also, besides this also includes the operating system, which, for example, has a very high code base. And for example, if there is a bug inside of the operating system, this could compromise the trusted app very easily, even though the app itself was considered to be secure. All right. And trusted execution environments exist to kind of as a countermeasure to such privileged attacks. So, for example, if we deploy an app on a TE, we again have all of the other entities as well on the cloud, beside like the other apps that other users deploy or the operating system. However, now the app itself is no longer accessible directly to the OS, because it resides, for example, in a different memory space that is separated from the OS. And this is enforced using a small addition to the firmware, which is called the security monitor. And this security monitor configures some trusted hardware that is deployed on the system and that enforces this isolation between the app and the operating system. All right. However, we can see that there is another attack vector that is not really covered with, and these could be, for example, some bugs that reside inside of the firmware. So let's take a closer look of what we can actually find in such a firmware. So we already know there exists the security monitor. However, there's also many other functionalities. For example, the firmware could also perform some power management of the platform, or perform some interrupts, some interrupt configuration, or also host some specific drivers that are necessary to launch the firmware on that platform. And the problem is now, if in one of those elements there is a bug present, it could compromise the execution of the security monitor and could also then eventually compromise the security of all enclaves that are present on the platform. And we did a small survey of different firmwares that are available for RISC-V, and we see that with time they grow, also because more and more functionalities or drivers are getting added to the code base. And unfortunately, for example, if we take a closer look on OpenSPI, we can also find that some bugs were discovered in the past These are most usually some memory corruption attacks, ranging from buffer overflows to null pointer dereferences or incorrect masking. So the idea of Dorami is to introduce some kind of privilege separation inside of the security monitor. And the idea is that we contain all operations that the firmware usually is doing inside of its own space, and contain all operation that the security monitor has to do inside of its own space as well. And additionally, with Dorami, we want to prevent that the components that the security monitor uses, like the trusted hardware for configuring the isolation, is also usable by components inside of the firmware. And the general concept that we want to introduce is compartmentalization. So on the left-hand side, we see a typical software stack as it would be deployed with TEEs on RISC-V, where the security monitor is part of the firmware. And with Dorami, we would like to put each of the firmware and the security monitor into their own specific compartments. All right. So let's take a look at the contributions. The overall question that we want to solve is how can we achieve privilege separation within the firmware? And we want to do this with three principles. First, we want to use existing hardware that exists on typical RISC-V machines to do this kind of privilege separation. Then we want to support existing TEE runtimes that exists for RISC-V so that they can be deployed as with Dorami without any additional changes. And also we want to put Dorami's isolation techniques inside of existing security monitors, for example, the Keystone security monitor. All right, so before we start with the design of Dorami, let's take first a closer look on RISC-V's security architecture and how it could be used to build enclaves. And first, I would like to present PMP, which is short for Physical Memory Protection and part of the RISC-V privileged specification ISA. So here on the bottom, we see the full range of the DRAM memory as we would find it on a machine. And this memory is typically separated into different memory regions. So for example, the operating system gets its own memory region, then the firmware, and then there could also be some read-only memory. And what PMP allows us to do is it can be used to assign memory access permission to software that operates in the S or the U mode. So for example, the firmware can configure this PMP and can give the operating system its own memory region, all access right, read-write executable, but resist access to its own memory space. So for the firmware memory space, it gives the OS like no access privileges, and for the ROM, it gives it only like read privileges. And this PMP is configured using so-called PMP config and PMP address registers that are CSR registers and present on the RISC-V CPU. And additionally, PMP also has some priority matching. That means where we can, when we configure each of this region, which with one of those, with tuple of these two configuration registers, we can also assign priorities. So for example, if there is an overlapping region, the first matching PMP configuration would be enforced by the CPU. And again, I want to emphasize that this permission system is usually only enforced for the S and U mode. So usually the firmware or everything executing in M mode would have all access rights to all memory on the DRAM. So now the question is, how can we build enclaves using this technology? And on RISC-V, we have various implementations here, various implementations for TEEs. Here are two examples, Keystone and Penglai, which use existing features on the CPU to build enclaves. And the key property is usually that to build the enclaves, these TEs create a mirrored or a separate memory space next to the operating system. So there is an enclave runtime and an enclave payload, each executing in S mode or in the U mode. And in the firmware, usually there's a small software component deployed that is configuring this separation and this isolation. And PMP is used as the isolation primitive. So how does this work? Here we again have our memory layout where the firmware and the security monitor have their own region, and the OS also has its own region. So to create a new enclave, the OS reserves some specific memory space, fills it with data that the enclave is supposed to be running on. Now, in order to execute the enclave, what happens is that the OS calls into the security monitor, and the security monitor then switches or flips the permissions of both memory regions. That has the effect that now the enclave can access its own memory region, but the OS is prevented. But the memory region of the OS is prevented from being accessed by the enclave. So can we use PMP to create or to build Dorami? So the main issue with just PMP is that it doesn't have the notion of least privilege. So in the M mode, every access into S and U mode memory, no matter how it is configured, will always succeed. So that means that the security monitor can always access each memory region, and also the firmware can access each memory region. Furthermore, we have the issue that all components in M mode can also configure how they want the access permissions to these regions using the PMP config registers. So that means that, unfortunately, as a candidate for compartmentalization in M mode, PMP doesn't seem to be a very good candidate. However, RISC-V recently ratified a new extension to ePMP that is called Enhanced PMP. And what it does is it strengthens the boundaries between the SU mode and the M mode. So if we again take a look on application isolation between an operating system and an app, there we usually have some kind of protective layer between the OS that prevents it from directly accessing SU mode memory. On Intel, this principle is called SMAP or SMAP. So what that means is that, for example, if an application gives a pointer that is kind of malicious to the OS, and the OS tries to dereference it, it will fail automatically. So it's prevented from directly accessing lower privileged memory. The OS would first have to give itself the permission to access this memory as well. This principle ePMP brings into the relation between SU mode and M mode on RISC-V. So here, again, the firmware or the security monitor would not be able to access all memory regions, again, of the lower execution modes. It would have to give itself explicit permission first to do that. Additionally, ePMP also deploys the notion of data execution prevention, or write XOR execute in M mode. That means that M mode's own memory regions can no longer have read-write executable permissions. So how does this look in the scheme? Here we again have our memory layout. And first, the change is that now the configuration inside of the PMP registers is now per mode. So that means if we give a configuration in this register, we also have to give the mode it should be active for. This automatically means that accessing this specific memory region from another mode is always is always prohibited. So if we now have a region here that is configured read-write executable for the OS, the firmware cannot automatically access its memory region, and vice versa as well, as it also was in normal PMP. So yeah, the first change here is that now firmware can not have read-write executable regions. So these memory regions need to be split up. That also means that the firmware needs to have its code and its data in the physical memory separated from each other. So now the question is, can we maybe use ePMP to achieve privileged separation inside of the M mode? And the answer to that is maybe. And that brings me to the design of Dorami. So as I explained in the beginning, we want to compartmentalize the firmware and the security monitor, so that, for example, if we have a bug that is present in the firmware, it does not have any effect on the execution of enclaves, because the security monitor would not be affected by them. All right. And the key principle is that we want to do this compartmentalization using enhanced PMP. And I want to elaborate the design of Dorami in 4 steps. So first, when we want to do this kind of compartmentalization, we need to take a look at the existing code bases. So right now, the security monitor is an extension to the firmware and essentially part of the firmware's code bases. So that means first there needs to be some kind of boundary drawn, because right now the SM, for example, uses some kind of functions that the firmware provides. And yeah, here we see an example of a control flow graph. So this needs to be separated. So now some functions that the SM used from the firmware need to be placed into the security monitor as well, so that we have 2 distinct code bases. And the idea is that, by that, we allow SM to perform all of the PMP and enclave management, and the firmware by that has all of the other operations that it previously performed, but now, just with 2 separate code bases. All right. The next step, we need to form the actual M mode compartments. And if we take a look on the 2 specific code bases that we just formed, the problem is still, if we place them inside of the memory, they still both execute with M mode permissions. So there needs to be some way of separating those 2 memory spaces of the firmware and of the SM, so that they can no longer directly access each other's memory. So for example, the firmware cannot change anything in the memory of the security monitor. And again, Dorami wants to use some existing technologies like ePMP to partition the 2 memory spaces of the SM and of the firmware. All right. The next step is to deprivilege the firmware compartment. And the thing is, because we are executing inside of M mode, both entities are now isolated from each other, but they can still both use all of the instructions that are present in the M mode. So let me show you what I mean here with a small example. Here we have like 2 small code sets of the security monitor and of the firmware. And so, for example, the security monitor has some functions to configure the PMP isolation or to run some enclaves. And the firmware also has some functions to, for example, change some PMP settings or do some other stuff. And now the security monitor somehow needs to ensure that although itself can access the PMP management functions, it needs to prevent the firmware from doing so as well. And it needs to check if the firmware is actually adhering to not using those functionalities. Right. And the next point is that when we establish those compartments and when we when we cleared the firmware from using those instructions, we need to somehow find a way of communicating with all other entities. So we need to define a way of switching from the operating systems or from enclaves into the security monitor and also into the firmware. And also we need to reason how we can transfer some data between all of those entities. Last but not least, Dorami also needs to reason about security of interrupts. That is because, again, firmware and security monitor execute in the same exception level, and there is no real hardware mechanism that automatically, for example, turns interrupts off or on when we switch from one to the other, as we would have, for example, between SU mode and M mode. So because of that, the security monitor with Dorami needs to ensure that the firmware cannot use the interrupts to exploit the security monitor. Let me show with a small example what I mean with that. So on the left side, we again have a small code base of the security monitor that again does some isolation and have some functionalities to switch into the firmware or handle exits from the firmware into itself. Now the firmware has some functionality on its own. And for example, it could modify the exception or the trap vector. And also it could schedule some interrupts that would be triggered at some point in the future. So what could happen is that, for example, some code exploits a bug in the firmware and places the address of the configure isolation functions from the security monitor as the target for the trap vector, and maybe also specify some other registers with some parameters to this function. And the exploit as well schedules a timer to be triggered in the future. So what happens now if the firmware exits back into the security monitor, the timer might be triggered and executes actually the function that the exploit wanted to be executed inside of the monitor. So it uses some kind of ROP primitive. And the security monitor therefore also needs to prevent these kind of attacks from happening. However, I will not go into the details of that in the scope of this talk. More of this can be found in the paper. All right, so let's start with forming the M mode compartments. So here we again have all of the components that we already saw earlier: firmware, security monitor, operating system, and enclave. And each of these components have a requirement for storing some memory. Again, M mode needs two memory regions because of the separation of code and data. Now, for that, Dorami needs to choose some kind of memory layout. And here we have an example placement on how this could be stored on the memory of RISC-V. And we see here that the security monitor actually has a second memory region. We will later refer to this as the SELI port, but for now, we will not go into the details of that. So if we have this memory layout, we need to kind of change the access permissions based on where we are executing. So for example, the OS only needs to access its own memory, same for the enclave, same for the security monitor, and also the same for the firmware. Now let's take a look on how we can build this using PMP configurations. So here we again have some access control configs. Right now the firmware and the security monitor are still in one configuration. However, we can just deploy additional regions where now each of these have their own specific memory region. However, at this point in time, both of them are not really isolated yet, because both of them could still access each other's memory, because both of them are in the M mode. So what needs to happen is that, for example, while the SM executes, all code and data of the firmware is set to not being accessible. Then when the SM wants to switch into the firmware, these permissions again need to flip. So now the firmware code and data needs to be accessible, but the security monitor once needs to be denied access again. And when we switch back from the firmware again, this flipping needs to happen. All right. So how can this be configured using PMP? And for that, let us take a look on the actual PMP configuration registers for that. So as I mentioned earlier, we have PMP address and PMP config registers. And let us start with the PMP address registers. These are essentially 54-bit registers where the range of a region is stored. And so in legacy, RISC-V, what would need to be done to configure this register is first need to establish a base address of a region and a size, convert this into a format that the PMP extension on the processor understands, and then write this into the CSR of the specific PMP region. What is important here is that this cannot be done directly with the CSR register. It first needs to be done on a general purpose register that is then copied using this instruction here into the PMP CSR. So with Dorami, this can be shortened because during compile time, it's already known which configuration is going to be written into the registers, so it can already be pre-computed, and then on the switching, it can be written into the specific registers. Right. Now, let's take a look at the PMP config registers. And here we see that those actually bundle 8 different region configurations in one big register. And each of these region configurations consists of 8 bits that specify the permissions, for example, read, write, executable, and also the mode it's supposed to be accessible in, for example, here with the L bit. And now if we want to update, again, PMP config 3, which is present in the PMP config 0 register, what first needs to be done is, again, copied out the full PMP config register. Then in the copy, those 8 bits need to be cleared, then stored with the new permissions bits, and then this copy of the PMP config register again needs to be written from the general purpose register into the CSR. Now in Dorami, again, this can be shortened because for M mode, all required configurations are known during compile time, so it can be placed just by loading a specific value into a general purpose register and then writing this into the config register. All right. Now, to summarize, what needs to be done in order to do a switching between the enclave and the M modes, or the switching to the compartments. So when we have an enclave, first it can perform an eCall into the security monitor. The security monitor automatically receives its own memory access permissions because of the switching of the privileges. Enclave was executing in SU mode. Security monitor is executing in M mode. And then when security monitor switches into the firmware, it changes the configuration with the instruction I just showed. And then on the way back, when the firmware exits and goes back into the security monitor, again, the specific configuration is written into the register. And then on the MRED, the security monitor again applies the enclave's memory access permissions. However, we see that this instruction might not entirely be safe. And the reason for this is that it can be used as what we will refer to as a gadget. And this brings me to the second point, where we deprivilege the firmware compartment. So here, again, we have this, this set of instructions that would need to be performed by the firmware when it exits to the security monitor. And this could be exploited. And for example, if there is some code inside of the firmware that loads some values into the general purpose register that is used by this instruction here. Here it's T0. Instead, it uses a custom value here, calls and loads then the address of the specific instruction here and jumps to it in front of it. It can, again, arbitrarily change the configuration of the PMP register. So in order to prevent this, two things needs to be done. So the first is that the SM needs to ensure that no such instructions exist inside of the firmware that can be used for this kind of gadgeting. And then it needs to find an alternative way on how it can perform the switching. And let's first take a look at solution number 1. So the idea, what Dorami can do is it performs a secure during boot, it performs a check of the code space of the firmware compartment. And essentially, what it needs to do is it needs to search for the pattern that we see right here, where some general purpose register is written into a PMP configuration register. So what happens is during boot, the security monitor, before the firmware ever executes, scans in 2-byte intervals its memory regions or its memory area, and only proceeds to start the firmware when there is no critical instruction found. If there is one, it immediately stops the boot process. So this works for 2 reasons. So first, we only have fixed instruction length on RISC-V. They can only be 2 or 4 bytes in length. So it's sufficient if the scanner scans it in 2 bytes intervals to cover the whole instructions in firmware's code area. And additionally, because there is no such instruction, it can also ensure that firmware can never really write into its own code section or execute its own data section, because again, there is the memory is deployed such that both is not possible, right? Okay, this brings us to the second point that needs to be solved, and this is crafting an alternative way for performing this kind of switching. And these instructions, or the instructions that we need, is something that can always remove permissions from the firmware compartment, but never add any new permissions to it. And also, when this instruction is executed, it's executed in a malicious way. It should not be able to compromise the security of the PMP. Right. So are there any instructions that fulfill this requirement? And actually there are. So in the previous examples, we usually only use the first 3 opcodes that we can see in this example here, which are CSR instructions that take a register as a source. However, there are also CSR instructions that take immediate values into immediate values from the source code that are then written into the CSR register. And the good thing is, because these instructions exist, the value that will be written into the PMP register is always fixed. So no matter how, if the firmware would execute this instruction, it will always write the same value into the PMP config register. However, we have a small problem here, and that is that the operator of these registers is only limited to 5 bits. And as we saw earlier in the other slide, the actual PMP config register has a size of 64 bits. So this is not even sufficient to configure reconfigure one memory region if we put a fixed value here. But Dorami can still use these instructions. And let me show you how. So if we take a look again on the PMP config registers, we see that we can not only configure the first 8, but also put configurations inside of the next one, which are here in PMP config 2. And the idea is that when we write zeros into the first PMP config register, for example, we use this immediate instruction to write 0 into config 0, automatically all regions that were previously defined will become invalid. So the hardware will not consider the configurations anymore because the configurations don't exist anymore. Because of the priority matching, it will consider the first region configured with the next PMP config register, which would be region 8. And Dorami uses this to create this kind of co-isolation when it switches. So here we have a deployment of the 2 firmware compartments again, and what happens is with the first PMP config register, we configure while we execute the firmware, we configure the firmware region to have its own access permissions, so it can access its own code and data regions. However, the code and data regions of the security monitor are set to non-accessible. But however, in the second PMP config register, we configure the security monitor's code again as readable with the according access permissions. Now, what happens if the firmware writes zeros into the PMP config 0 register? It automatically clears all configs that have been covered with the first register, and now the access permissions that were in the second PMP config register allow access to the specific memory regions. So by that, when the firmware switches to the security monitor, automatically all access to its own memory region are revoked, but access to the security monitor's regions are given. And then, when the security monitor again executes, it fixes the access permissions and then prepares it for the next switch, for example, into the firmware. All right. And now the third piece that needs to be solved is how can we actually cross between the compartments and between the modes. So here we again have the overview as we saw it already earlier, where the enclave executes, it performs an equal into the security monitor, and then the security monitor switches into the firmware. So the most general way of switching from the security monitor to the firmware would be, for example, prepare the firmware's registers, then reconfigure the PMP such that it is to the view that the firmware requires, and then jump into the memory region of the firmware. However, because we atomically set the configuration such that the security monitor's memory region is no longer accessible, but the firmware is, we can no longer perform any jumps from the security monitor into the firmware because the security monitor's code base is no longer accessible. So how do we solve this? The idea is that the security monitor places its own code base directly in front of the code base of the firmware. So what happens if the security monitor executes the function to reconfigure the PMP configuration? The instruction pointer advances, and it directly starts the execution of the first instruction that is present in the firmware. So the permissions for the memory access permissions switched, and the execution of the firmware automatically starts. So we can kind of slide from the security monitor into the firmware. Now the question is, how do we go back from the firmware into the security monitor? And the problem is we already used the sliding mechanism from the memory region was already placed in front of the firmware, so we cannot really slide anymore back into the security monitor because there's no more region. And this is where the SALI ports comes in. The SALI port is essentially another memory region that is trusted and part of the security monitor, and that is placed immediately at the end of the firmware's memory region. So in this example, the firmware can now slide into the SALI port, which is now trusted to perform again the PMP reconfiguration. Then it jumps to the main security monitor component after it reconfigures it, and then the security monitor can again start the execution of the enclave using, for example, an MRET. And here's a schematic overview again. So security monitor executes, its memory region is unlocked. It uses a sophisticated PMP instruction because it is trusted, but still slides into the firmware to perform this atomic switching of the access permissions. Then the firmware is executing. Firmware now uses this CSR write immediate instruction to clear the first PMP config register. Then Celliport executes because it now has its own access permissions from PMP config 2. And then then the Celliport reconfigures the whole access permissions for the security monitor, jumps back into the security monitor, and the security monitor can again perform the execution. All right. So now that that has been solved, how can we actually transfer data between the compartments and the SU mode? Again, let us take a small look at an example where the operating system performs an eCall to the M mode. So in this example, the M mode lands in starts immediately the security monitor, and then the security monitor could, for example, either directly call an MRED because, for example, the OS wanted to launch an enclave, or it could slide into the firmware. Now, what happens when it slides into the firmware? It first sanitizes all the registers from the OS and only passes the registers that are needed to fulfill this kind of request from the eCall inside of the firmware. Then when the firmware exits, it again slides into the security monitor, and the security monitor again only places the registers with the result, for example, according to the SBI specifications, and then returns to the OS. And what's important here is that neither the OS nor the firmware can call each other directly, and they also don't have any direct interaction with each other. And as I said, all the information is only passed via registers. Either when the OS performs an eCall, or, for example, when the enclave performs an eCall, all the information is only available via a register and via a specific interface there. Now, the transitions that are affected with Dorami is listed here. And again, I will refer to the paper where we provide a bit more information on what needs to be done to support all of those transitions with Dorami. Right. This brings us to the implementation of Dorami and its evaluation. So we implemented 3 functional prototypes of Dorami, 2 on an FPGA and 1 on an emulator, and we implemented 1 performance prototype using the Hi5 unmatched board. Unfortunately, there was no ePMP compatible board available at the time when we did the paper. So we resorted to a PMP only board, but we emulated additional rights to ePMP if it was necessary. And with the functional prototypes, we verified that all the isolation and what is necessary is functional. And for this prototype, for the performance prototype, as per the design, we needed to configure 6 PMP regions for the general boot environment. So 5 for M mode, where we have 3 with security monitor and 2 with the firmware, and then 1 for the operating system. And then we deployed keystone enclaves, which require 2 PMP regions per enclave. All right. So the first test that we wanted to do was to evaluate what general implications Dorami has on the platform. And we see that the one-time costs range between 0.4% of an overhead for boots, and for enclave operation around 15 to 17%. However, we also see that equals are getting very expensive with an overhead of 290%. So to find out what the actual implications on the on the execution this overhead has, we performed some benchmarks for CPU and memory tests using the RE8 benchmark suite. And there we compared the execution within the host operating system and inside of an enclave between legacy keystone deployment or keystone with Dorami. And then we observed an overhead of about 0.18% in general execution and 0.42% when executing inside of an enclave. However, these benchmarks don't really show I/O interactions, for example, interactions between an enclave and the host OS. And for that, we launched the FSCQ large file benchmarks, which performs read and write operations with the host OS from inside of the enclave. And there we observed, when we wrote different file sizes, we observed that the throughput only really decreases if the chunks of the file sizes is low. So with increasing chunk size, for example, with 512 kilobytes, sorry, it nearly goes to 0 to 1%. So it doesn't really have a big effect for that. And then lastly, we also performed some case studies. The first case study was the dark HTTP web server inside of an enclave. And there we observed also, again, only a big overhead for smaller websites, for example, with 1 kilobyte, and it was almost 0 as the website size increased. And the second benchmark was a MySQL database server that was launched inside of an enclave, and there we saw an overhead of around 5% when comparing Keystone and Dorami. Right. Last but not least, we also wanted to take a look of what an overhead we could expect when launching, when bringing ePMP into the processor. And here we synthesized multiple CPU configurations. For example, we added ePMP support to the Rocket Ship CPU, and we synthesized NoLV in 2 pipeline modes. One with single issue and one with dual issue. And we can see that the more complex the pipeline is, the more impact or the more resources need to be in use if using ePMP. And additionally, we also try to estimate some runtime overheads of regularly switching ePMP configuration as it would occur with Dorami. And for the Rocket Ship, we observed an overhead of around 5.5%, and for NoLV of 1.9% for single issue and 0.5% in the dual issue synthesis. All right, now to conclude this talk, could we achieve privilege separation with the firmware? So we showed that we used ePMP to create an isolation within the M mode. And this isolation create essentially these 2 compartments for the firmware and for the security monitor. We used the existing TE runtime from Keystone to launch enclaves inside of the parallel SNU mode. And we used the security monitor from Keystone to implement our additions of Dorami and to do the isolation enforcement inside there. Okay, so with that, I would like to conclude the talk. You can find more information about Dorami in our paper that is now available on arXiv and will be published next year at Usenix Security. And additionally, we also released a website where we will put more background information about the project in the future, and will also in the future put some code to our implementations there. Thank you very much for joining, and I'm happy to take any questions.
Thank you very much, Mark, for presenting and for all the details that you cover. So, folks, we are now, if you want to speak verbally and ask questions, go ahead. I think you are allowed to unmute yourself and ask questions. You can also write the question in the chat, and you can read that so the presenter can answer. So, any questions for them? Not sure if Andrew Dell, not sure if you have any question for them at this point. One question in the chat. Oh, just a text. Okay, one question.
How does the instruction filtering work? So yeah, this is a good question. So I think this refers to was the slide. This refers to, where is it? I think here. So yeah. So we filter the instructions essentially according to the, sorry, is this does the instruction filtering work? The deprivilege. Okay, I'm not fully sure. So you mean, I guess, this here.
Yeah, I think they're referring to the scan before you start the firmware.
Okay, yeah. So this is probably then this one here. So yeah, essentially what happens here is the firmware needs to, so the security monitor kind of needs to prevent the firmware from ever executing any instructions that have this pattern here. And so what happens is the security monitor is the first entity that is in the boot chain. And before it ever launches the firmware, it scans the memory of the firmware if it has any of those patterns. So it just checks like the opcodes or like the binaries or like the binary opcodes of the firmware if there is like like this instruction present, or like if the bits are set such that it represents an instruction where it's like a CSR, write, whatever, and one of the PMP registers, so PMP config, PMP address, and so on. And yeah, it checks that there is no instruction where it like writes from the general purpose register into a PMP register. So yeah, essentially, yeah, it checks all byte tuples in the memory. Okay. I hope this answers the question. Okay. Is it workable both on RISC-V 32 and RISC-V 64? So we only implemented the design on RV64. One limitation that you have with RV32 is that there per PMP config, you only have I think, if I remember it correctly, you only have 4 memory regions here. So there would need to be some way of kind of making it compatible with this. I think it might work if you set the other registers to like if you were, for example, cover PMP config 0 and PMP config 1 with the firmware permissions, and then the other one with the masking for the SALI port, it might work, but we haven't tested that, so that would be future work. How does that security monitor impact security? How does that work on dynamic code? So yeah, dynamic. So I'm not fully sure what the first part meant, but dynamic code essentially would not be possible that easily. So it depends where the dynamic code would need to run. If the dynamic code would run inside of the security monitor, then the security monitor would be considered trusted, right? And it could just execute it. However, if the dynamic code were to run inside of the firmware, before it would ever be executed, the security monitor would have to do like a scan of the memory again. But we have not included that in the design, so that would also have to be looked into if that's possible in a secure way. All right. Did you measure for how many cycles interrupt need to be disabled when switching from F to P and vice versa? From F to P and vice versa. So yeah, that's a good question. So the point is with interrupts, I didn't go into much detail for that in the talk, but with interrupts, essentially that there wouldn't be a big window necessary for disabling them from when entering the SM from how's it called, from the firmware, because while the firmware is executing, only the firmware itself would have like a target of the trap vector. So another constraint that we have that I also didn't go into much detail here is that the firmware cannot modify the trap vector. So it would be present by the, like it would be set by the security monitor before it switches into the firmware. And then part of this binary scanning would also check that the firmware never changes anything in the M trap vector. So essentially, every time when an interrupt would be triggered after the firmware switches into the security monitor, it would execute a function of the firmware. But because the firmware's function is no longer accessible, it will essentially loop the CPU in an inaccessible state, because it would try to access the trap handler, right? And then the trap handler is not accessible, so it would cause a PMP access violation, and then it would never be able to recover from that. But these details are in the paper. All right. Given that Dorami relies on RISC-V for intra-mode isolation, how does it ensure atomicity and eliminate time of check, time of use vulnerabilities during ePMP reconfiguration? Time of check, time of use vulnerabilities during ePMP. So the atomicity of this is achieved by always using the like always writing a specific or like a fixed configuration into the PMP config registers. So for example, if where was this? Here. So for example, when we do a switch with Dorami from the security monitor to the firmware, there is a fixed, like the whole range of the configuration here would always be overridden at once. So there wouldn't be any window where it's like open for both or open for firmware and SM, so to say. So every time when we do the switching, it ensures that each of the region, like the security monitors region or the firmware's region, are only accessible without any, or should I say, without any overlapping window. Right.
I think it's also, I'm sure this is somewhere in the paper, but I'm sure you also disable interrupts and guarantee that the code you're about to execute doesn't trigger an exception.
Yes. Yeah.
Okay.
So is this like static code analyzer in the hardware? No. So the static code analyzer is essentially a piece in the software that would execute before the firmware ever executes. So it's part of the initialization routine of the security monitor, and for example, would be triggered like directly in or after the first stage bootloader. So that's then doing the scanning, launching the security monitor, and then the security monitor starts the initialization of the firmware.
Great. Oh, one more question arrived.
Okay. Have you considered if any changes in PMP and or ePMP extensions could simplify or improve the implementation? That's a good question. So let me think about this. I mean, it's hard to say. So the problem is that the PMP right now does not have like multiple identities, so to say, built into. Whoops, where's the presentation mode? Built into the configuration space. So, for example, it can't decide when you like execute inside of a region that this region now identifies with this execution identity. I don't know how to put this. For example, it does not automatically know if you are executing inside of the firmware that then it should only apply these specific memory access permissions, and then when you switch into the security monitor, that it should then automatically just apply these memory access permissions. So it kind of does not have this how should I say this idea of what is currently executing. And if that could be automated, I think the switching could also be a bit easier, because then essentially then the PMP wouldn't have to like protect itself, so to say. I don't know. Okay.
We have, I believe, one last question.
Okay.
From Alvin about CSR.
Do you have any detail on msec-config CSR? What's the value of the msec-config RLB? Yeah, this is also a good point. That would, of course, also be checked during the boot check. And of course, the RLB bit needs to be set because we need to change the configuration of the PMP permissions that apply to the M mode. Otherwise, it wouldn't be possible to change them anymore. So yeah. msec-config bit, RLB bit needs to be set. Then there was this one bit for what's it called? MML bit needs to be set, and MMWP should also be set. Yes.
And I think that was the last one. Any more questions, folks? Okay. So I would like to thank you, Mark, Stravos, and Shrita for all the work and for presenting your future paper to us today. That's really helpful, and I believe your next step is to join one of the technical under the task groups, right? To have more deep conversations about the work you're doing. So thanks very much. Thank you very much. Feel free to, contact us if you would like to present in any other technical session. The recording will be available soon, and I'll let you know when that's public available at our YouTube channel. Thank you very much.
Thanks, Stefan, for hosting us, and thanks everyone for a lot of detailed questions. If you have more, feel free to email us, and we should be able to get back to you.
Thank you very much, everyone.
Thanks. Bye.